Hey everyone, here are our notes on Unit 4.7, inverse trig functions. So just as a reminder, inverse function, these are the notes that are going to show up at the top of our page here. I'm going to talk through these kind of definitions here, highlighting anything important, but then we'll kind of jump back and fill in as we go. If you need to, please feel free to pause and just scribble down these definitions and all the details here. Otherwise, just follow along. First, we are dealing with inverse functions. They are, so first, inverse relations are functions if they pass the horizontal line test, HLT. So what the HLT tells us is that the function, a function's inverse is a function if it passes the horizontal line test. But we know that trig functions are going to be problematic. They are going to look something like this. They are definitively going to fail that horizontal line test. So if we want to use inverse relations in the world of sine, cosine, and tangent, we have to restrict our domain. Sine, cosine, and tangent are not one-to-one functions. They are functions, but their inverses are not. So as a result, we need to restrict their domain. So here are the restrictions we apply. For the sine function, our inverse sine has a restricted domain such that our domain is always between negative pi over 2 and positive pi over 2. This is the angle over that interval whose sine is x. Let's look at the graph of sine of x just to make sense of maybe why we made the choice to restrict our domain in the way we did. So here we can see sine of x, that's our green graph here. And what we need to include are all possible outputs. So our lowest possible output would be -1. Our highest possible output would be +1. So in my estimation, when this decision was made, we, mathematically speaking, decided to include the first quadrant, right, from 0 to pi over 2, in all three functions. But we had to choose wisely about how we chose the other half of our domain, right? Because if I kept going in the positive direction, I have issues, right? I would fail the horizontal line test even still. So in order to meet all the possible outputs for sine, we just started at negative pi over 2. So from negative pi over 2 to positive pi over 2, we get all the possible outputs with none repeating. So our domain goes from negative pi over 2 to positive pi over 2. Now with cosine, it's the same idea here. We're using inverse relations. For cosine, our domain must exist between 0 and pi. Let's go back to the graph while we're keeping it in mind here to make sense of why. Well, here I have cosine of x right there in the middle with that purple graph. So again, if I look at our first quadrant here, 0 to pi over 2, I have values that are useful. But if I went back to negative pi over 2 like we did for cosine, again, I have issues, right? If I look here, I would be failing my horizontal line test. So we want the first quadrant, and in this case, we're going to have to include the second as well. Now with this area from 0 to pi, we have our high point of +1 to a low point of -1. Finally, our third interval is used for tangent. Its interval is negative pi over 2 to positive pi over 2, excluding the endpoints. We'll just take a quick look at the graph to make sense of it. Well, what we can see here is that we do get the full measure of tangent on that interval, right? We would have sketched in some vertical asymptotes here. But between those two intervals, we have every possible value for tangent. With sine and cosine, we had half of a complete period. For tangent, we have a complete period. In both cases, that takes pi radians. The endpoints are excluded here because the endpoints of negative pi over 2 and positive pi over 2 are asymptotes and cannot be included. So when we talk about inverse trig functions, the biggest thing that throws people off is the domain restrictions. We need to know when each function is usable. I'm going to move over to our blank copy of our notes here. I'm going to ask you guys to try your best to try to use your calculator or your unit circle to evaluate these three examples. Let's see how they went. So on the first example, they are asking us, when does our tangent equal root 3? Well, that happens when y over x equals root 3. On our unit circle, this happens when we get root 3 over 2 over 1/2. Right, that would simplify down to root 3. So where on our interval for tangent between negative pi over 2 and positive pi over 2 does tangent equal root 3? Well, it happens when tangent's positive, so I know I'm in the first quadrant. And then I need to figure out, well, when do I have a y value of root 3 over 2 and an x value of 1/2? That happens when my angle measure is 60 degrees, or if I was in radians, that occurs at pi over 3. There is a place on the unit circle in the third quadrant where tangent would equal root 3. However, because we're using the inverse trig function, we must get an answer in the first quadrant. That's the only time the tangent is positive over our allowed interval. Our second example here, I'm going to use my calculator. I'm going to find the angle whose sine is 1/4. And what I found when I plugged that into my calculator, I get 14.48 degrees. That value is definitely on the interval of negative pi over 2 to positive pi over 2. And finally, our third example, this is a two-way street here. This can come in radians or degrees. Again, I'm using my calculator. I would get 0.747 radians or 42.78 degrees. Now we know from the cosine function, there are an infinite number of places where our cosine function equals 0.734. But we are always, when we use a calculator, our calculator has these domain restrictions built into it. So it knows not to give us an answer like, say, 138, it's supplement, right? In each case, our answers will always be on the expected interval. Now, one thing we do with inverse functions is we use them to undo another operation. So this chart is in here for when we observe, the sine of an angle whose sine is. Well, when do we get the answer that we're looking for, right? Well, that only is going to occur when that x value is between -1 and +1. This next one, the angle whose sine is sine of x, that's only going to equal x on the interval given. Let me just create an example of what I'm talking about, how this wouldn't work. So the angle whose sine is the sine of, let's say, let's pick a value outside of this interval. Let's say 135 degrees. That is outside of our pi over 2 interval. I'm just keeping it in degrees here. I think it's a little bit easier to keep straight. So if we were to simplify this, this would be the angle whose sine has the same sine of 135. I just rewrote exactly what I had. Excuse me. The sine of 135, that's a y coordinate in the second quadrant. That's going to be root 2 over 2. When I simplify even further, the angle whose sine is root 2 over 2, well, when I use that inverse sine, it wants a value between negative pi over 2 and positive pi over 2. So the angle on that interval with that sine is actually a 45-degree angle. So it's possible that we have the angle whose sine of a sine value that we don't actually get the number out that we might expect. I don't think we need to go through every single example here, but this table is useful for identifying when things will work and when they won't. What do I mean by that? Let's look at some examples. So here, I'm just trying to keep the table available for us. Here we have the cosine of an angle whose cosine is 0.7. Well, that looks an awful lot like this. As long as my value of 0.7 is on the interval of -1 to +1, then my answer here is simply 0.7. Looking at number 2, I need an angle whose sine is the sine of x. Sorry, the angle whose sine is the sine of pi. Well, if I try to evaluate this, what it's going to do first, it's going to work inside out. It's going to be, let's just look at our table, and we can see that we should have values that are between negative pi over 2 and positive pi over 2. Now, we don't. So our answer is going to be more unexpected, I guess, than what we would think. But really, we're looking for the angle whose sine is, well, we can evaluate the sine of pi. That's the y coordinate on the left-hand side of our unit circle. That is 0. So the angle who has a sine of 0 with our interval, keeping in mind, the angle on this interval that has a sine of 0 would be 0 and not pi. One more of these examples. Number 3, this is again going to be working with the highlighted rule up above. They are asking us the cosine of an angle whose cosine is -1.2. Well, there is no such thing of an angle whose cosine is -1.2. That is why we have this restriction right between -1 and 1. There is no solution. It is undefined. There is no trig function, no cosine that gets a result of -1.2. There's a few more examples on this first page. I think we'll work through 4 and 5 and then pause this video where we are. So here on number 4, we need to find the cosine of an angle whose tangent we know. Well, if I'm using the inverse tangent, I know that I am in the first quadrant. How do I know this? Well, my tangent is positive. If I'm using the inverse tangent, I'm positive in the first quadrant, negative in the fourth quadrant. So if the angle's tangent is 5/12, then the hypotenuse here is going to be 13. So really, I've identified the angle as theta, and I've built the triangle related with the information given. Really, what I'm going to try to find is the cosine of theta, which is going to be adjacent over hypotenuse, and it's going to be 12 over 13. So in a problem like this, where I have an unfamiliar sine or tangent, I definitely recommend building a triangle. Number 5 will be another example of that. So on number 5, they want us to take the cotangent of an angle whose sine is -1/3. So I'm going to work inside out here. I know that sine exists between the inverse sine exists from -pi/2 to +pi/2. So if sine is negative, I must be in the fourth quadrant. What do I know about this triangle? Well, I know that its sine is negative 1/3. The hypotenuse is a distance and will always be positive. The negative must come from my y coordinate. I'll have to use the Pythagorean theorem here. 1 squared plus b squared equals 3 squared. So b squared equals 8. So the length of b is 2 root 2. That is our horizontal side length. All right, so now I have this triangle. Theta is our reference angle here. So I am trying to find the cotangent of theta. Right, by constructing that triangle, I've created a triangle with theta in it. Now I'm basically trying to identify the cotangent of theta. That is going to be the adjacent side divided by the opposite side. So that's going to be 2 root 2 divided by negative 1, or in the simplest form, negative 2 root 2. We're going to pause there, and we will move on to part 2 for the back half of these notes.